Well, hi everyone, and greetings from Northern Michigan. This is Bob the Science Guy. Welcome to the first live stream from the new observatory dome. I'm actually out in the dome tonight, so kind of doing this from the field. Going to give it a try and do this live. In order to do this tonight, what I'm going to do is I'm going to go to the Minor Planet Center, and I'm going to find some comets for our location tonight. Other observer services, observer target listing. Going to put in our latitude and our longitude. Going to grab 50 comets and hit submit. Now we should be zeroed right in on the comet. Let's just see if we can see it real quick on a quick look. Should be right in the center. That it? Could be. This is just a 4-second exposure, so it's not really giving us too much information. So what we'll do is we'll sit down and we'll connect our guiding and start some guiding here. Okay. All right, there we go. So it'll guide. Now we'll go over here and let the magic happen. Going to do a series of 1-minute exposures and live stack them. We're at unity gain, which means that 1 photon equals 1 electron on the sensor. That's a unity gain on this camera is 100. So I like to set it just over that at like 102 to make sure that we're right at unity gain. And there's also an enhancement on the chip that makes it much more sensitive at above 100 than it is below 100. So we're going to let this thing cycle 1, and then we're going to stretch it a little bit. We're going to balance it and stretch it and see what it looks like. Tonight we're using the RASA 11. It's on a Celestron CGX-L mount, which is a really nice mount with a capacity of 75 pounds. We're going to guide with PHD-2. Our camera is the ZWO 6200 MC, which is the one-shot color version of the ZWO 6200, which is their top-of-the-line camera. We are going to get rid of Sigma clipping here. Sigma clipping is kind of difficult when you're dealing with things that are moving, like comets and asteroids, because it's designed to minimize things that change from one frame to the next. Like if you had a series of subframes and a satellite went through one of them, it would recognize that satellite trail was different than all of the others, and it would de-emphasize it. It would basically just make it go away. Well, unfortunately, asteroids and comets move as well, and it makes them go away too. So there's a satellite trail right out here on the side. I don't know if you can see that. It's on the left side there. Now we're going to move this a little bit to kind of get a uniform dark background. Kind of like that. And while we're at it, we're going to go ahead and have a look at the center of this image at about 200. No, that's probably a little too much. Let's go to 100. But the comet is going to be right in that area right there. And as you see, we've got nice round stars. And even looking up in the corners, really not all that bad. Just checking out all the corners here. See, there's a satellite trail right there on the right. That red dot is a hot pixel. Our comet should be right in here. I don't see a tail just yet, and I don't see any fuzziness around it. But right now it's kind of a waiting game. We're going to get a bunch of what we're going to do is we're going to get a stack of images. Just making some small adjustments right here. Come on. I'm using a trackpad with this, and I don't seem to have as good a control as I would with a mouse. And that's unfortunate. Leave it right there. Have a look up here at 100%. I don't see any fuzzies in there, but we'll find out. When I'm done with the stack, what we'll do is we'll run it through the Tycho software, and we'll see whether or not anything's moving. So you see our total RMS here is less than 1 arc second. Anything less than 0.5 is acceptable. We're running a total of 0.13, and that's 0.75 arc seconds. This is the guide scope. It's a little blurrier than you would see on the main scope, but that's okay. What it does is it just finds the center of brightness for each star and tracks that. Makes minor adjustments to the tracking to keep that right in the crosshairs. And here we'll just let this thing stack. You see, we've got a tremendous field of view, and this is a color camera. Our focus is less than 2.5 right now, less than 2.6, which is pretty good, which means that we have nice round dense stars. We should be able to pick up asteroids with this. This week we did. One of my benefactors donated a ZWO 6200 monochrome camera to me, which is going to be 4 times as sensitive as this one. It won't have the pretty colors in it, but that's not really what you're doing when you're looking for asteroids and comets. You're looking for movement, and you're looking for very tiny, dim objects, and that'll really bring those things out. So let's go see what we got going. Let's pull that down. Just want to make sure that I'm still getting, yeah, that's good. And there we are. So now we're just going to kind of let it go. Let's put on some tunes and see what we can do. Here we're taking some data, and let's see how many images we have. We have 48 images. I decided to have a quick look at 30 images to see whether or not we could spot anything. The purpose of this evening's observations are to, 1, find this comet, C2020R7 Atlas, and verify its location and orbit. The second thing that I wanted to do is just have a look at the rest of this field and see if I could spot any asteroids in it. Now, we don't really see the comet very well. You know, it's very, very dim. And I don't really see anything in here that would suggest to me that it's the comet. However, when I run it through Tycho Tracker, which is my asteroid software, I am able to locate the comet, and as you can see, it's right here in the crosshairs. Now what I did was I went ahead and I got some observations of that, and I put those observations into the MP checker, the Minor Planet Center checker. And what it did was it took my observations, which are right here. So here's the object. These are the observations, the orbital elements that I took. That's the magnitude, and that's my observatory code. And it compared it to known objects in the database. And the only object that came up was the comet that we were actually looking for, which is C2020R7 Atlas. And the thing about it is these offsets that you see right here, these are what's different from my observations to the expected observations. And as you see, I'm dead on. I nailed it. Initially, what you do is you process all of these images, you line up the stars, you equalize the exposure, and then you stack them. Then the computer will go through and look for anything on those images that's moving from one image to the other. And it picked up on this one right here, and it's very confident that this is an actual object. You see the quality of the image is 60, and the probability or confidence is high that this is an actual detection. Now looking at it, you see it's kind of a fuzzy object. This is what comets look like. You know, they're basically balls of ice with gas around them. Now they're different than stars, which are pretty well demarcated here because I've got really good focus. Asteroids show up very well demarcated like these guys as well. Comets, on the other hand, are fuzzy. And that is a fuzzy object. It's magnitude 16, which really isn't all that bad. And, you know, it's a dim object, but it should be one that I could easily detect. So I was able to actually pick it up with only 30 images. I'd like to see what the full stack of 60 images looks like, because I think that we may pick up some other objects as well with 60 images. The more images you have, the better signal-to-noise ratio that you have. You get a lot, you know, you notice a lot of the noise in the background here. This granular, fuzzy-looking material, you know, this kind of, it looks like a rough surface. It looks like it's blue sandpaper there. The more images you have, the more uniform blue this will be and less rough appearing it'll be. You'll also probably pick up some additional objects out in the list of, when it looks at these tracks right here. It'll try and actually assign an object to the track based on what the orbital elements of that track are. It'll compare it to the database, and it says that it thinks that that's our comet. It looks like a comet, and when you look at my observations, they match the predicted orbit of the comet exactly.